Hello. Hello.
Hello.
Oh,
Oh,
can you hear me? Tata, okay, so the idea of this part is just to check in on lab 1. I don't know how many of you have done it or have attempted to do it. I started solving it just now just to present something right now, but I realized that there was a mistake in one of the equations. So maybe some of you got to that mistake and were a bit confused. Was that the case? Did anybody attempt to run the lab one? Okay, I see no answer. So I will assume that most people did not and got focused on the homeworks. Okay. Okay, some people did. So in the first part of the lab, we are solving the differential equation, the derivative of y over t equals lambda times y. We all know has an exponential solution. So we are implemented we have implemented here the Euler method. Here there was a little mistake for anyone who has the notebook open right now. It probably says something like this. In your notebook it should say y minus 1, not I alone. This is needed for the plot to make sense. Okay, let me run some cells here. And let's talk about a bit about this section here for those who maybe couldn't quite follow it. This is supposed to be kind of a simulation of how the differential equation packet works. So the idea in this part is that you just define the step of the method that you want to use and just insert it here, and this will take care of all the evolution, right? So in this case, I have defined here the function Euler step that does a single Euler step, right? It takes y and it applies y plus dt times f, which is the Euler step. If later on I want to use a different one, a different method, I just define, for example, rho ejecuta 2, rho ejecuta 4, whatever I want, and I can simply change this function here, change any of this part. Part defines the problem that I want to solve. So here in the f, I put the f that I have on the right hand side of the equation. The y0 would be the initial data, the interval would be the time, the interval, and par are any parameters f needs to run. So for example, in our case, this would be lambda. Okay. And then we have my ODE solver, which takes the problem, takes the method, takes the delta t, and simply solves it, and has a delta t defined just in case. Okay. Um, this will be the same thing that we will use when we use the differential equation package, where, as you have seen, you define the problem, and then you take a solver and solve the function, and you also have to, this part of the package is already inside, right? This part in differential equations, you do not create, it's already stored. Although you can create your own methods if you want to. Okay. So here is the main issue I had. I put in the WhatsApp. The original function was written like this. Tab here it was t and lambda. When it should be lambda and t, the order of the parameters. This has to do with how the here the function in other steps expects the solution, the parameters, and then the time, and it was the other way around here. So please change this. I will change it later on and update it so the plots make sense. You have to run this. So maybe you don't have this plot in the Python, in the Jupyter notebook that you have. This is the plot that you should actually have when you correct the problem, right? So the first problem we put here was to try to see what happens when we try different values of delta t, what happens to the solution. So we know that the solution is underestimating the exact solution. So we want to know that as we get smaller delta t, we get closer to the actual solution. And this is what I am doing in this step right here. So this is what we are expecting to see, okay? So in this case, we are iterating over some different values of delta t, which go from 1, 0, 0.2, 0.1, 0.05, 0.005, right? And then we are using our solver Euler step and plotting what happens with several delta t, and we see that as the delta t gets smaller, 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 we get closer and closer and closer to the solution. So this is delta t equals 1, so very crude approximation, and this is delta t equals 0.005, much better, but still we can see that's not the exact solution, okay? So later on, and this is very important, we want to calculate the Q factor of the Euler method. So if you recall, when you have to calculate the Q factor, you need 3 values of delta t, each one half the value of the previous one, right? So we do a quotient between the difference of each values of delta t, and this should give us the conversion order of the method. Did you all follow that part in the lectures? Do you understand what the Q factor represents or what it means? Anyone here can also answer. Okay, yeah, it's the conversion factor to the p, exactly. So if our method is order 1, we would expect the Q to be 2. If it's order 2, we would expect the Q to be 4, and so on, right? So this is what's expected in this step here. We are choosing different values of n, which is exactly the same as choosing different values of delta t, because we are using the same limits for the integration region, right? So we are integrating from t equals 0 to t equals 4 and choosing different values of n, which result in different values of delta t. So this is what we are expecting to see. We take n equals 201, 401, and 801, and this will give us 4 different values of theta t, and this part here is where we calculate the Q, right? So we subtract the solution with the low resolution, and we divide by the solution with the high resolution, right? With this difference here, and this gives us a Q factor of 1.951339997. So it will most likely not be equal exactly to 2, right? We expect this to be 2 because we expect Euler to be linear in when we are talking about the global convergence, but it will not. It will never be exactly 2. It will always be something close to what we want, because of course there are higher order terms in the error that will always make this fluctuate a bit. Sometimes it will be below 2, sometimes you will get something over 2 if you have a different problem and something like that. And now in the following part, we want to implement a second and fourth order Runge-Kutta method and create them, right? So here it should be RK2, RK2. Okay, I have to update some things here. I see another mistake here. So here, what we are doing is creating these step functions that we want to do. So this is exactly the same as we had here with the Euler step, which in this case gives a 1 Euler step. We want to do something that gives 1 Runge-Kutta step, Runge-Kutta 2 step, or Runge-Kutta 4 step. Okay. So in this case, I went over. Runge-Kutta 2 steps, we have to define the constants k0 and k1 that we saw previously, and do the update. And in Runge-Kutta 4, we have to define 4 constants, k0, k1, k2, and k3, and then do this operation to do 1 Runge-Kutta step as we have seen before. Okay. So once you have implemented this method, we want to evolve and calculate the Q. So this is what we are calculating in this case here. For example, this is the Q for Runge-Kutta 4. So we are doing exactly the same as we had before, and in this case we are using Runge-Kutta 4, and we see that the value of Q is now 15.86. So this is very close to 16, which tells us that P is equal to, or approximately, 4. So this confirms our suspicion that Runge-Kutta is a fourth order method. This will be very useful later on to calculate the conversions of several methods. So this is very important to keep in mind when doing stuff. Of course, you always have to be careful on how to do this. So imagine that here I had put 400, 200, 800 here, something like that, and I try to run this here. Okay, in this case, okay. So if I'm not careful with the, in this case, let's see if we can make it. Where is it? Sí, no sé. Why is this happening? why I'm trying to trigger an error here, but not this error. Why isn't this working? So let's do like this. Let's try to solve. Just I don't know why this is not what I wanted to do, but just what I wanted to mention is that you have to be very careful with the delta t that you use. Sometimes you don't realize and you are not using exactly half the delta t, or you are not evolving up to the exact same final time. So if you commit the little mistake, then the order conversion may not be accurate, right? So that's just what I wanted to show you, but I don't know why it's throwing an error about something being an integer, which shouldn't happen. So I will leave it there. I will then try to show you, okay? So later on, up to now, is everybody follow me? I guess this part is quite simple. So now this we go to this equation that is very important for you to understand, right? So in this case we have the derivative of y over dt equals y minus y squared, okay? So it's useful to first, in this case we are working with a solution for which we actually have an analytical solution, right? And we see that the right hand side of the equation is actually smooth. It is actually a polynomial, a second order polynomial. But that doesn't mean that the solution will be defined for all time, and this is the case in this problem, right? So the solution, the actual solution to this problem is this one here, right? So the solution to this equation will be something of the form to the exponential of t divided by, where is the divided by some constant plus the exponential of t. This is the actual solution of the problem. So this will have a solution for all time unless c is negative, right here, okay? So if you choose a negative value of t for a finite time t, this will diverge and we'll stop having a solution, okay? So this is what we always have to be careful when, and this is what we mean when we say that we can always find a solution for an open interval around the initial data, okay? So we know that we have a solution close to certain initial data, but not for necessarily for all times after that, okay? So this is just to see what we would expect here, and these are the solution for different values of the initial data. So we have two fixed points. One is y equals 1 and the other one is y equals 0, and here is where we can see again the stability of certain fixed points. So 1 is a fixed point that is stable and 0 is a fixed point that is unstable. As soon as we depart just a little bit from the solution y equals 0, we get a curve that goes away and converges to y equals 1. Okay. And in this case, here is what here is the solution for two methods. This is the solution for the Euler step and the Runge-Kutta step. Okay. In both cases, we get to the solution. Remember that Euler here we expect it to be stable. Euler is not that bad when we are kind of decaying, but we still see a big difference between Euler and Runge-Kutta. The dashed lines will be the Euler and the continuous line will be the Runge-Kutta lines. So this is kind of what we are expecting to see and to analyze. But you can see that it's not really that bad. Okay. Now if we try different initial conditions, but with the initial condition being negative, which is the second part of the problem, which is optional, we will get something like this. Okay. So you see that for very close solution to 0, we get there, but as soon as we start going out, this starts diverging. Okay, and here we are seeing a time interval between 0 and 1. But if we try to change this time interval here and try to do something a bit larger, we see that the solution diverges numerically. This is 10 to the 255, so this is a very big break for the solution. And this is what we would expect, because recall that the actual solution does not exist. So this is not really a problem of the method, this is a problem with the problem that we are trying to solve. We are going far away from where the problem is actually valid, from where we can evolve. Okay, so we always try to stay where the problem actually has some actual solution. Okay, so for example, a bit more. See, immediately after 1.1, this diverges brutally. So we will never be able to go past that point. Okay. Up to up to this point, is everything okay? Because in that case, I wanted to try to solve with you the some of the system of equations. I was trying to implement it right now, but I hadn't finished doing it. So I wanted to talk about a bit about the Lotka-Volterra equations, which is actually number 4. Exercise number 3 is actually very similar to the previous one. Okay. We have this system of equations, the pendulum or the with small amplitude, or the linear oscillator, which is actually very common. And the Lotka-Volterra equations are a bit more fun, maybe, to understand what's going on. So this is the Lotka-Volterra equations. Describe a prey-predator system where we have two populations. One, X represents a prey population, the number of prey of a species, and Y represents the predator. So the prey is being eaten by the predators. So in the prey equation here, for anyone who doesn't know about it, okay, how can I erase this here? We have this term, which is an exponential term, and this here, which is an interaction term. So what this equation is telling me is that imagine that there are no predators here. So y equals the predator population. So we remove this term because y equals to 0. So we will have some exponential growth. So this is telling me that the prey population will continuously grow if I do nothing about it. So this assumes that it has infinite resources and it just starts reproducing and it grows exponentially. Okay. In the other hand, in the predator part, we have this and this. Again, in this case, imagine that there are no prey. So if there are no prey, the predator population will always decay. So this is why we have a negative term here. It means that the predator population will die out because it has nothing to eat, it will die. On the other hand, this term here, it has a product, tells us that the prey population will decrease as the more predators there are in relation to prey, and the other way around. The predator population will increase if there are more predators and prey. If there are the more prey there are, okay? So this is what this is telling us, okay? So the predators decrease the amount of prey and the prey increase the amount of predators. And all these constants need to be positive, okay? So this is what we are trying to evolve here. Okay, how do I... ese, ahí. So this is what we are trying to evolve here. In this case, we also have a conserved quantity, this v here, okay? This delta x minus gamma times logarithm of x. So this is there always is some conserved quantity with these equations that will have to remain constant during the evolution, right? For example, in this case, we have the energy to be constant. In this case, we have this constant here, which is v. And if we want to solve this equation, dv over dt equals 0, and I invite you to do it, you simply have to, okay, we can do it here. Okay, so v of x, y equals delta x minus y natural logarithm of x plus beta y minus alpha natural logarithm of y. And if we try to do the derivative, dv over dt, it will be delta times dx over dt minus, how can I go to, let me see if I can go to, okay, no. Delta times dx minus dt minus yeah, here we will have dy over dt times logarithm of x plus minus y times dx over dt over x plus beta times dy over dt and beta times dy over dt minus, okay, how do I, se trabó, ahí está. Where? This is a gamma. Ah, yeah. That's the mistake I made. Okay, and besides this equation just broke down. Let's do it again. dB over dt. We have to take here. This will be equals to delta dx over dt minus gamma times dx over dt over x plus beta times dy over dt minus alpha times dy over dt over y. And here what we have to do is simply replace the values that we have here, okay? So dx over dt will be delta times alpha x minus beta xy minus gamma times dx over dt will be equal to alpha x minus beta xy over x and so on and so forth. So when you do all this calculation, we can start crossing out terms and we will get that this equation will have to be constant over a certain amount of time, okay? So what we are trying to do here is now to define these equations here, okay? We have dx over dt, dy over dt, and this is what we are doing right here. We are defining the Lotka-Volterra function that takes a y, takes some parameters, takes a time t, and returns dy over dt. And this is what is expected to do, okay? So here we have defined alpha, beta, delta, and gamma, and we put them right here. And let's see if this equation is okay. So alpha x minus beta times xy, okay, here, okay, perfect. And the other one is delta times, okay, xy minus gamma times y2. So this should actually work, okay. So now we will simply do some evolution. We'll try to copy paste, and it's likely that we will get some kind of mistake here, some broadcasting mistake. Yeah, it's gamma instead of y, as someone pointed out. Okay, here we go. So here in this case we will put Lotka-Volterra, okay, and here y0 will have to be some initial data that we want to try out. y0 equals, in this case we are asking it to be 1, 1, okay, so we will put 1.0 times 1.0, and here we have some values. Alpha equals 1.5, beta equals 1, gamma equals 3, and delta equals 1. So we will try to use here the help of Copilot and put 1.5, 1, 3, and 1. Okay, this should work. And here the parameters will have to be P equals to alpha, beta, delta, gamma, right? Problem here, put local Volterra. Here. Okay, so it seems to have evolved. Perfect. So we can now plot here, plot t, y, and see what's happening here. So we did a bit of evolution and we saw this plot here. We will try to put here some labels to understand what's going on. Label equals prey predator. Let's just complete all of this. Okay, here. So prey is in blue and predator is in this kind of orange. And we see that the predator population starts to increase, and then here it starts to decrease again, and here is the prey population is starting to go down. It started to go up a bit, but apparently there were too many prey and started dying out. Okay, so let's try to do this with a bit more time interval. So here we had the interval, I don't know what it was, but it was taken from a previous problem. And as the interval here, we are supposed to use 0, 20, okay? Equals 0 times 0, 20. And we evolve this. And here is where we have our actual population pattern, okay? So what we see here is that the amount of predator increases with the amount of prey, but there is a point where there are too many predators and too few prey, so the amount of predators will start to go down because they don't have enough to eat. So here you see that this is going down as the prey population is very low. But at a certain point, the prey population starts to grow because there are not as many predators, and this makes the predator population go back up again. Okay. What we wanted to see now is if this constant here, this value v here, is actually constant during the evolution. And this is something that you will most likely try to do a lot of time when you are trying to evolve a system and you are trying to see, okay, is my solution actually good? Because sometimes you know how the solution will look like because somebody else did it before, because there is an analytical solution, but most of the time you do not. So sometimes you have to rely on certain things that you know how to remain constant when you do the evolution to see that you are actually on the right path, okay? To see that you are not breaking some fundamental property of the problem that you are trying to solve, okay? So if this, for example, if you are trying to solve a pendulum and you see, this is oscillating, okay, nice, but then you see the energy of the problem, and you see that the energy starts going up and up and up and up and up and up ad infinitum. So then you will have some kind of problem. Sometimes what you want to do is at least to ensure that the solution, that the energy, for example, does not increase over time, so it remains constant, what at least goes a bit down, but not increase, because the more energy you have in the system, the worse it will get. Okay, so let's try now to define this function v and see what's going on here. V of x of y, let's see, because the solution is already function v of, let's put here u we will define some parameters p here, and okay, let's try to do it, but return, and we will have to do delta times, and here we do x equals u1 and y equals u2, delta times x minus gamma times y minus gamma times logarithm of x minus beta times logarithm of y plus alpha minus beta times y plus alpha times logarithm of y. Let's see if this is actually working. Okay, here we go. And now we'll try to plot here plot t and some other value here. We'll put b applied on y times p. Let's see if this works. No, it's not doing the broadcast. There's the bp of y equals b of y times p. I think this solve it. Okay, let's do the simple solution. B list equals zeros length y size y would be equal to I want to just plot the potential. Okay, values E equals B let's see if this works. Not ln, is log, the function. And I think here we go. So the potential is not working. So maybe there was a mistake on how I defined the potential. Delta minus plus minus plus So this will be actually the potential that we have. So this looks like something very weird that's not really that's not really constant, but you always have to try to also look at the y-axis on the scale of this part here. So we see that overall it starts to decrease, and this is not really changing that much. This is changing in a very small interval around 4.0 that's not even registering in the labels here. This is actually what we can do is try to do here is see what the maximum of Belize is. And we see that the maximum is 4.000068, something like this, and what the minimum is and we have a very good conservation of this quantity here. So this is working very well. Now what would have happened if here, instead of using Runge-Kutta-4 that we used here, we have tried to do the other method, for example. Okay. So in this case, we actually have some. We actually see some of the cycles, but we see that because there is a real ancient value of the problem, there's a real part, you see that each peak of the predator population is larger and larger and larger each time. So this is actually not a very good solution. Okay, and we can actually see that reflected in the conserved quantity here. So if you try to see what V is for the Euler method, we see that it starts increasing. So this is something that you always have to try to check when you are trying to do to see if your solution is good or bad. It's trying to see what conserved quantity the system has and see how it behaves. Okay. On the other hand, the problem also asks us to plot the phase diagram of X versus Y. So we want to see how many predators there are for a given prey population here. So what we are going to do is plot here Y here it is. Copilot really knows what you are trying to do. It's just I assumed I was trying to put the plot phase. So what we are doing here is taking the vector y and plotting the first component and the second component. And again, here we were using the Euler method, so let's go back to the Runge-Kutta-4 step. So this is what we are actually seeing, right? So this is the amount of prey and the amount of predator in a loop. So we start with very small amount of prey, and this starts growing up exponentially until there is a point that the predator population starts to increase. Okay, and the prey population will actually start going down while the predator population is increasing, and then again the predator population will go down until the prey population can start increasing again. So this is the cycle that we are seeing. But we can do this with several values of the initial data. Okay. So again here, this is what we are going to do now. Okay. So when we solve a problem, C, command B. In our problem here, we have a certain initial data y0, and this is what we are going to try to change. Try different values of the prey and predator population. Okay, so right now we will do y0 list, let's do like this. For prey in, and let's do it like this. Okay, let's do 0. Let's do it like successing. Ah, okay. So what we are trying to do here is change the amount of prey in each iteration. So we start with 0 prey, with 0.1, then 0.2, and so on until 2. And we solve for that particular initial data. And we will do some empty plot. And we will see how the cycles go. In that case, display PLT, comma, PLT equals plot right now. So we see there are several behaviors, so it's always the same, this kind of oscillation. But instead of plotting this, let's try to plot again this here. Y here. So we see that if we start with different initial data, we will get different curves, right? Yeah, so this is okay, perfect, okay. So we will get different curves with different initial data, and there is a fixed point right there we will have to get to, where if we start there, the prey population will get completely evened out, and you can calculate that very easily. You just have to take this equation here and set it up to 0, and this will give you a matrix here with alpha, beta, minus gamma, and delta, and when you solve this, it will give you the value of x and y that you need to have for this to be equal to 0. This is the point that we are actually seeing here. You see that there is a point line here that goes down up to 0 very quickly, and this is actually the case where we started with 0 prey, because if we start with 0 prey, the prey population will never increase. The prey population cannot appear out of nowhere, and the predator population will therefore decrease because it has nothing to eat. So this decaying exponential will be reflected this way on the graph. Okay, so we try to do a bit more here. Let's try to get up to 3. Let's see if we can. Okay, we got closer to the point here. So this is probably 0.4. Okay, 0.3. Okay, so I was just trying to do some plots to see if we got closer to the point here. And of course, you can always try to change some of the variables here. For example, you can try to make the predator-prey interaction not to be as harmful for the prey. So that would be changing the beta, for example. And if we try a smaller beta, maybe we get a different behavior. So we get something that's much sharper. Or if we get a different value of delta, maybe we get something that looks a bit more like a sine wave. We get this kind of plots here. So if you want, you can always try to play around with these solutions. So is it clear kind of how to implement the function, how to solve this problem? Are there any parts in the function that I defined that were not clear? Or maybe some things that I did in Julia that you didn't quite get? I'm talking, for example, on how I plot things, stuff like that. Does anybody have any doubts on how to do it? Okay. Does anybody need help plotting in Julia in general? Okay, so there are no questions. At least we can then check two different problems here. I don't know if you want to check, for example, the problem number 3, or if you'd like to check problem number 5 or 6. Is anybody interested in solving one of those problems? You can write on the chat or just open the microphone. The stability region is interesting. Okay. So the fact that you need to use the, could we see number 5? Okay. So here, numerical stability. So let's return to the equation from the previous notebook we have here, and so the equation lambda equals -1 in time interval 0, 20. Is there a way to summarize the way to plot stability regions of integrators? So we have a notebook here. Oscar just went out, so I don't know where he has it in his computer, to try to see, to try to plot the instability region. But you can always find it online. You can always check the system that you are trying to solve. Let me try to. This is a different computer from mine, so I'm not sure. Yeah, so here you can try to see. Yeah. Okay. See. Yeah. So let me see if I can find it here, because this is what we were seeing in the. This is what we were seeing actually in the previous notebook. Maybe it's, I can find it here. Okay. No. Leco, ¿dónde tenés el stability region? El notebook de stability region, así lo vemos. Porque está preguntando sobre las regiones de estabilidad.
¿No está ahí en el lab 1?
Sí, pasa que no sé manejarme con la Mac, entonces.
A ver, déjame quitar.
So he's talking about how in Rugen method there are analytic regions, but if we have an exotic method from the zoo of Reula, we need to be able to plot the region, right? Where is it? There is one. So let me try to revisit this notebook, what it does, but it actually tries to plot the instability region. So what the method here is trying to do here, this is just a simple equation where we have an initial data, right? An exponential function, lambda times u, of lambda, f of u, lambda, and t returns lambda times u, okay? So what we are trying to do here is just to try to see what the stability region is, and to do so, we simply evolve the problem for several values of this mu here, okay, which will actually be the lambda, which will actually be maybe the lambda times the delta t that we will try to solve later on. And if we do just one step of illusion and the solution starts to increase, then this tells us that there is this is unstable, and if it stays the same or tries to decrease, then this tells us that the method is stable. Okay, so this is what this is doing here. It's just doing a single step in time with a delta t and trying to return 1 if it's stable and 0 if it's not stable. Okay, so this is what this notebook here does. Okay, so we take here, for example, the Euler method, and we have defined here Euler, and we do a map of x and y here. X will go from 0 to -5, and y will go from -4 to 4 here, and this will be the real and imaginary parts. And this is what we are doing here. We are plotting x, y, and this is a function that takes x and y and gives us the stability indicator, right, of this value here. This is x plus y times one imaginary unit, so this is a complex number, and using the Euler method. So in this region here, when you do that, you will get an exponential decay. So you will get a smaller value of y when you evolve. In the other regions, you will get a larger value of y when you evolve, right? So this is exactly what we are checking here. We do a little step, and that's it. And this is using the ordinary differential equation package, right? So now, later on, we do it with Runge-Kutta, for example. We do just a single step in Runge-Kutta for several points here, and we try to plot a heat map, and this is where we get this region here. Okay, so it's actually quite simple to do it numerically. You just take the scheme that you want to check, and just do a little time evolution for a certain value of lambda for the exponential growth, and see, okay, is this actually bigger or smaller than it was before? You can see it in the notes in the book. Later I put it in the WhatsApp so you can see it. Maybe we can put here, for example, I don't know if what other methods we have here. This is Hoynes method. Okay. This is TSIT5, for example. This is the stability region of TSIT5. Okay, so you see where you are, and we can just take any method that we want. This is a special case of third order Runge-Kutta method. Okay, so let's take any let's try to take any method here. For example, here let's see if differential equations Julia integrators or the solvers here. Full list of methods. So here we have a lot of, here for example we have a 7th order Runge-Kutta method implemented here. Which one? Which one? Sorry? The TSIT5 or? TSIT-PAP8. Okay. Come on, see. And here we put in the stability region. It takes a while, so quite large stability region here. So maybe we have to try to do x. What is x? Let's try to do it a bit larger. Equals minus 10, 0.2. And here let's put 1, y, like this, something like this. Okay, I try to put a bit less of resolution, and was a bit too much. So let's see. So yeah, this is kind of a monster compared to the stability regions of the other methods, but you see that's actually very good, right? So this is much larger than that one here. Here we are going to from 4 to minus 4 and from up to minus 5 here, and here we have minus 7.5, and here we were, I don't know, minus 6, something like that. So that means that you can take a delta t a bit larger and it will converge, while the other method will maybe not do so. Okay. So here we want to return to the equation, for example, on the notebook, dy over dt equals lambda times y, and we try to solve the equation with lambda equals minus 1 in the interval 0.20, okay, and we want to try with Euler and Ruge-Kutta and just plot here, okay. So we will define here, we had before the exponential growth, so this is what we were talking about here, the stability region notebook, and just simply copy and paste the first problem here, okay. Okay, so here we had our little problem here. Let's try lambda equals -1 now. So this is a decay, and let's try n equals, okay, this is 101, and we see that we have our decay, right? So the numerical solution is the red one, and the exact solution is the green one, and we solve with n equals 101, and now we will try it with n equals 51, for example, and solve again, and we have a different worst numerical solution, which we would expect because we have a larger value of delta t, and we decide, okay, let's try to see if what happens if we continue going down that road. So 50, 30, 20, 10, 5, okay, 50, 30, 20, 10, and 6 here. Okay, this is getting worse and worse. What happens if we put here 3? Okay, so maybe we can go a bit, we should have one a bit smaller than 5 there, here, and like this. Okay, so here, for example, if we put n equals 5 and we try to solve this problem, t equals 0 between 20, that's why it wasn't working like I expected. I took too long. So there we go. So here when we put t equals 21, let's see how it was going. Okay, so for y equals 21 is actually when we at this point where in the first iteration of the Euler method, for example, we got to the solution y equals 0, and from then on it will just stay at 0. And if we go a bit over and we go to 1, suddenly we have this solution here where we start oscillating, right? So it's not actually that, okay, it always decays, but the better delta t I use, even we get to a better solution. If you choose a bad delta t, if you choose a delta t that's too large, okay, then you will have stability issues, and this is exactly because you are outside the stability region. So here lambda is negative, so if you have delta t equals 1, maybe okay, delta t equals 1 and lambda equals -1, so here we would be around here. delta t times lambda, we will be around here. But if you try to take a larger delta t and a larger delta t and a larger delta t and a larger delta t, then you will eventually go out of the stability relation this way, and the solution will not converge, right? So here, if we try to, for example, use Runge-Kutta step, and we put again, okay, here we saved it, okay? Here suddenly we are actually back again in some kind of acceptable solution, and this is happening before because in the Euler method we were around here maybe, okay? We had a very large delta t that took us out of the stability region. But when we try to do that in the Runge-Kutta method, then we are around here. The stability relation is a bit larger, so the Runge-Kutta accepts a worse delta t value and will still give you something that is stable. But it will only help us so far, right? So if we continue to do the same thing with the delta t value, with the Runge-Kutta, and here we go to 5, 6 here, then we see that we start to diverge in a problem where we were supposed to be smaller and smaller each time, okay? So this is the importance of the stability region, okay? And there is no one delta t value for all problem. It also depends on the problem that you are trying to solve, right? Because it will depend on locally what the lambda value is. So, for example, here we were doing with Runge-Kutta, we were doing, for example, with 41 points, works perfectly for this value of lambda. But if suddenly we try to use lambda equals -4, which is a much sharper exponential growth, it continues to work, but now we try -10, and suddenly we get these diversions again. And we think, okay, our problem is good, actually we have an exponential decay, I expect Runge-Kutta to simply go there, but if you don't choose the delta t accordingly to the value of lambda, then you will get this kind of issue, okay? So does everybody understand what's happening here in the stability region? I don't know if this kind of problem, for example, is better for you to visualize it, right? So here, for example, we will try to use a bit, again, we will use a complex value. Let's try to do it, for example, with lambda completely imaginary here, and try again to understand the stability region here. So here we have this, let's go back to Euler. And we try to solve, and here we have to put a real everywhere, so we get the real part of the solution, I guess. Here, let's see if this works. Yeah. Float. In Euler step it's not actually working, because maybe Euler step expects something. I don't think so. Okay, maybe. Where is it going? Ah, here. Okay, here we go, right? So here we have this solution. Is actually kind of a sine wave, and this is the numerical solution, and this starts going up and down, and it starts getting larger and larger and larger. So this is what we were talking about in the stability region, right? So our eigenvalue here, lambda equals, is the imaginary part. And we are in the Euler method. So here what we actually have is delta t times lambda. So no matter the delta t that we use, we will always be outside the stability region. If we were just a little bit inside here, then maybe, okay, we can take a delta t small enough that the method converges, right? But otherwise, no matter the delta t that we use, we will always be outside, right? Now, if I take here, for example, 0.1 minus imaginary part here, something like this, for example, let's try to solve this problem here, and we do so. Okay, there is a bit of decay here, but it's very, very small. But now we will use a larger value of n, and actually we see that the solution, the numerical solution, is not good, but it's actually decaying too. So this is actually also stable. So here we are starting to get inside the stability region right here. Okay, and the good thing about the Runge-Kutta method, as we were talking previously, is that now if we do this here, imaginary part, and here we put Runge-Kutta step, we have a very good solution. Let's put here 21, for example, something like this. We have a good solution here, okay, that stays within the bounds of the original solution. It's not going out, it's staying there, because again, we are inside this region here. So we have our eigenvalue that's completely imaginary, and we are still there. We are still in the stability region, right there, okay? So this is 0, okay? So if we are here, everything is okay, and we can take a smaller delta t, and we will still be in a stable region of the method. We will even be stable for some small positive values of lambda, of the real part of lambda, okay? But again, if we take a very bad delta t, then we will go outside this way. So if we take here delta t equals 5, n equals 5, something like this. Okay, the Rungecuta method will also explode because now we have gone out of the stability relation, but this way. Maybe if we use this method here, we can still try to evolve a bit, but it will be stable. It doesn't mean that it will be a good solution, it will be a bad approximation maybe. So is there anything else that you want to discuss, to talk about? Any other particular problem? I hope at least this clarifies a bit the stability region, what we are talking about, and how to interpret that weird plot that we are doing. Of course, later on, when you are trying to solve a partial differential equation system, then this y will be just the value of y will be the evolution variable that you have in all space. So in the other side, you will have this weird matrix here. This lambda will not be a value, will be a weird matrix, which is what we were seeing right now in class. We were seeing the d minus d plus d0 operators, and those operators have eigenvalues, and we have to make sure that the delta t times those eigenvalues are inside the stability region. So if the eigenvalues have a positive real part, then there's nothing we can do. It will just grow and diverge. While if they have a negative part, then we can do something. And if they are purely imaginary, then we can do nothing with Euler, for example, but we can do something with some Rungecuta schemes, for example. Okay, so I hope this is useful for anybody who is having some issues with this notebook. Please, I will change it and update it in this afternoon, but make sure this has the correct order of the parameters. It should be y lambda t, not y t lambda. It should be y lambda t for everything to work. Otherwise, you will be plotting. This will try to put the t value here that has nothing to do with the problem. Instead of lambda y, you will be plotting t times y, and it will not work. So, if nobody has any other questions or something that you want to revisit, okay. So perfect. Okay. So there will some people will send the lab again with the correction because I made I'm truly sorry about that mistake. It got carried over from a previous iteration and I didn't catch it because there was an exponential growth. I just assumed, oh, this plot is okay, and now I see that it was plotting something else entirely. Okay. Are the labs and the homework mandatory? Are the labs and the homework mandatory? Yeah, they are mandatory. So at least attempt to do them. Okay, it's, at least try to do it, and if you have issues with some parts, just say, okay, I couldn't finish this part. Can you explain it to me? There are certain banks that are optional, and don't be afraid to just copy and paste and just tell a bit about what you understand. Okay, for me the math homework is almost impossible, but the numerics are easy. Okay, so if you want, we can just talk about some of the homework problems later on. Which homework problems are you having issues with? Homework 1, 2, 3, or 4? Anything with topology. Yeah, okay. So Enrico, ¿te parece en un momento we can do something about talking about topology, because the homework on topology for some people are maybe it's not as clear. So yeah, so okay, we can talk about topology. We will, I don't know. Tomorrow morning we can talk about a bit about the topology homework and try to understand it. It's those are things that maybe look simple for people who are already experienced, but when you think about it, it actually took thousands of years for humans to get around topology. So it's not, if it takes a bit more for some people or less for others, it's quite expectable for this kind of problems. Okay. So tomorrow we will revise a bit about the topology homework, stuff like that, so we can all be in the same page. Okay. So if nobody has any other questions, we will. Okay, I am not used to the math formalism. Okay, so tomorrow we will talk a bit about the some of the homeworks and try to solve at least some of the parts. So we get the math formalism. Okay. Okay, sure. I hope this lecture was useful to you, and we will see you tomorrow. Okay. Bye.